Hey guys, so this is our last section of physics that we're going to cover here in chapter 26. And this is, I just want to hopefully give you a taste and an understanding of how physics has changed in the last 100 years. 100, 110, 20 years. For a long time we had the Newton's laws of motion, and really Newtonian physics was this foundation that we just always lived on. But with advancements in technology and understanding and really just some brilliant minds putting their focus on physics, the way that we understand modern physics as opposed to what you'd call classical physics, which is basically what we've covered up to this point. Modern physics is a totally different world. And it really comes around due to one big adjustment to the way that we understand the world. And it has to do with this concept of inertial reference frames. So think about, let me just pull up a picture here. All right, so in this picture we can see the person's going to drop a coin. And in both cases, if we look at different frames of reference, that coin, in terms of the car, is dropping straight down. But if I'm standing outside of the car and looking at it from, say, the Earth perspective, that coin doesn't fall in a straight line. It actually falls in a parabolic path, a projectile motion path, as it has horizontal and vertical components of velocity. Now, where Newton, came to his conclusions basically said that in this first case or second case, in either of these cases, we can't actually tell who's moving, okay? Because while we might say, it's easy to tell that the car's moving, the car could say just as easily, the driver in the car could say just as easily that I and the Earth are moving. If the tires were put, in neutral and there was no air resistance or anything like that, and the Earth wasn't initially spinning, right, and we gave the Earth a spin, or we think about putting the car on a treadmill, the treadmill's moving, but the car's not. Well, how's that any different? It's no different than if the treadmill's motionless, but the car is moving. See, who's moving is insignificant in Newtonian physics. It doesn't matter. It just matters that there's a relative difference in velocity. And that's all that mattered. So if we could figure out the difference in velocity or the difference in height, it didn't matter when we did projectile problems or when we dropped something from the top of a cliff. We didn't actually need to know what the height of the cliff was. We just knew its height difference to whatever the ground was below it. And so understanding this idea that frames of reference allowed us to just say, well, what's the difference between the two? And we're going to say that one of them moves or the other moves. And we didn't actually have to know who was physically moving. All laws of physics work the same. Well, that was great until there was this issue with a guy named Maxwell. Maxwell is the one who did all this work on the concepts of electromagnetic waves and electromagnetic forces and showing the relationship between them. He found that light is an electromagnetic wave, behaves as an electromagnetic wave, which means, and here's where the big question comes, if the speed of light is 3 times 10 to the 8th meters per second, and let's say that the source of the light is traveling away from us at 1 times 10 to the 8th, towards us at 1 times 10 to the 8th meters per second. Then is the actual observed speed of light going to be 2 times 10 to the 8th meters per second? In other words, could we ever get to a place where we could see light being slower because we're traveling at a speed relative to it? Now, if you think about throwing a baseball out the back of a truck, if I get the truck to go, 20 miles an hour back or forwards, and I shoot the ball or throw the ball 20 miles an hour out the back, the ball's going to drop straight down. This was the question that needed to be answered. Maxwell didn't say there was such a thing as relative velocity for these electromagnetic waves, but that was the question that needed to be answered. Is there a situation where at a certain speed of travel that the source of light has to have, that yes, 3 times 10 to the 8th is the actual speed of light, or is it always that way and the traveling object doesn't matter? It's essentially asking the question, I'm on a rocket ship, right? There's my rocket ship. Okay, and I'm traveling along, but it's dark out in space, so I have headlights. Okay, there's my headlight, and it shines a light, right? And it's traveling at 3 times 10 to the 8th meters per second, right? Boom. It's traveling really fast. Well, if it's traveling really fast, what happens if I'm traveling really close? Let's say I'm going 2.99 E8 meters per second. What will I see? Will the light be traveling? Will the light even get anywhere? The whole idea of headlights is that the light hits something, right? Maybe a person or something back here, and then bounces back, right? But if I'm traveling almost as fast as the light leaving the headlights is, well, am I ever going to be able to get the light? How much reaction time am I going to actually have? This was a fundamentally important question, and wanted to know, what is the circumstance when light actually has the speed of light of 3 times 10 to the 8th? Well, enter Einstein, and he does some really interesting thought experiments that change everything. His 2 postulates that come out of this special theory of relativity in 1905, he said, you know what? There are some things that are set in stone, and the speed of light is one of them. So first, he said, his 2 postulates. First, the laws of physics have the same form in all inertial frames, reference frames. Hey, you know what? There's no special reference frame. Laws of physics are the laws of physics, and they don't really change. But there is something that's constant, that won't change, that will then affect other things. He says that light propagates through empty space with a definite speed, c, meaning the speed of light, 3 times 10 to the 8th, independent of the speed of the source or the observer. This takes away this sense of, well, I'm only going 2 miles an hour compared to that car, so it seems like I'm not moving very fast. All of that is gone. He says, no matter how fast you're traveling, speed of light, speed of light. It will travel 3 times 10 to the 8th meters per second away from you, no matter how fast you're traveling. So what does that affect? What does that mean? Well, that actually means that concepts of time have to change. Okay? Whether you're going towards something or away from something, time starts to change. Now, when we're traveling pretty slow, time dilation is almost negligible. Well, it is negligible. But as we start to go faster and faster, we start to notice that clocks slow down, that other things change. And here's the basic premise of one of his big thought experiments. I think this was initially done with a thought experiment of a train, but this is a similar experiment that be done on like a rocket ship or something like that. So you have a light source, and the light travels up, hits a mirror, bounces back, and ticks the clock. Tick, tick, tick. Every time that light pulse makes it to the mirror and back. So there's a set distance. It has to travel that distance twice, right? Distance up, distance down. But we can figure that the time it takes between each pulse and the distance, if we take distance divided by time, that gives us our velocity of light. Boom, easy. Well, if the velocity of light is held constant, and we allow this rocket ship to travel really fast to the right, then the light doesn't travel just vertically. It has to also travel horizontally in order to cover the distance, both vertical and horizontal. That is a bigger distance. Now, if the speed of light is held constant, if c never changes, and c is the change in position over change in time, one of 2 things has to happen. Either the space that it travels has to be smaller than we thought, or the time it takes. Okay, we need more time in order to cover that same distance, right? And so this has to do with the concept of time dilation. And that instead of the speed of light being relative, which is what everybody thought was going to happen, said, oh, the speed of light, it goes faster if we're going faster. Einstein said, no, no, no. Light's not going to change. It's the time that changes. And so we start to get into this concept of what's called time dilation. Okay? What this is the observed time, or change in time, will equal the at rest time. So this is if you're not moving. Okay, so if you're not moving, that's how long it takes. So hey, 3 seconds here standing still on Earth compared to 3 seconds traveling at the speed or near the speed of light. Totally different. And we have 1 minus the velocity that you travel squared divided by c squared. And since this will always be number less than 1, because we're taking the square root of it, it'll always be less than 1. We know that the time observed will always be greater than the time at rest. So let's be really clear. Clocks moving relative to an observer are measured by that observer to run more slowly as compared to clocks at rest. So the velocity makes time slow down. All right, now obviously the bigger the gap in velocity, the closer we are to the speed of light, okay, then this fraction is going to get bigger, and this becomes closer. This denominator, if velocity goes up, then this fraction over here will drop in value, or will rise in value, until it's close to 1. So this denominator, as v goes to infinity, or goes, not to infinity, as v goes to c, the speed of light, this fraction, it goes towards 0. And anything, so some number divided by 0 will approach infinite. Okay? Right, if we divide by 0, we divide by 0, we get infinitely large result. And so we're starting to see that time will slow down and potentially stop. If we could ever go the speed of light, time would theoretically cease. Which is I think is a cool thought. This is our formula for figuring out how much time difference there is based on velocity. There's one other calculation that we're going to make, and that calculation is for length dilation. Oh, as a side note, Einstein had this proposed experiment it's called the twin paradox. You have 2 twins, and say they're 20 years old, and you're going to send one out on a spaceship traveling at the speed of light, or very close to the speed of light, back out to a star and back. You got to go on a little trip. Comes back. The Earth twin may have aged 20 years here on Earth, so they'll be 40 years old. But depending on the velocity, the space traveling twin would have traveled much less, would have had much less time pass, and might come back with only a year or so depending. That concept then, it's not just a thought idea, but a literal biological difference that happens as we travel at high speeds. Our own biological clocks would change and slow down as we travel fast. This is a really, really crazy thought, but it actually works out in principle. Atomic clocks run based on the radioactive decay of an element. So if you think about it, we know the half-life of certain radioactive elements. And so we know for a certainty, after experiment, we're certain that the biological or the chemical changes that take place in that radioactive material will happen at a certain time. And that's how atomic clocks are built. They're built, again, where this radioactive decay tells it to tick that clock. And so when we take those atomic clocks and we put them up in spacecraft and we travel as fast as we humanly can, and we're talking 7,000 meters a second and faster, we travel as fast as we humanly can, they don't keep the same time as clocks here on Earth, which is evidence and validation to the fact that all processes, physical and physiological and chemical, they all slow down at higher speeds. So these are some crazy things to think about, but I think it's important that you guys have a basic understanding that time slows down. And we use that in the GPS system. You know, those satellites are moving really fast relative to you. They have to keep time. Okay, they have to keep time in order to know where you are, in order to properly locate you. The other thing that we're going to talk about is length contraction. When you're traveling very fast relative to other objects, okay, things get smaller or narrower, if you will. That is to say, we end up with this equation here for length contraction, which is just that the observed length equals the at-rest length times, and then we're timesing by, oh, come on. And we're timesing by the square root of 1 minus v squared over c squared. Again, as we go fast, the length of objects is appearing to be shorter than those that are at rest. So length contraction. So not only does time slow down, but actually things get shorter. It's part of the natural inclination. So if you're flying past this painting really fast, it would not be as wide as it is. Now the height doesn't change unless we're moving vertically as well, right? And so it's all about relative to our motion. Which way is it going to change? Well, guys, there's a lot more we could talk about. We're going to stop there. Hopefully take some time and you work with those equations. But really, I just want you to take time to think about what impact that would have and what experiments would you want to do, given the opportunity to test things out. Like, what could you validate and how would you validate it? And you know, what does that mean for us if we were to say travel to another planet? You know, we know that it takes so long to get to Mars, for instance. But if we're traveling fast, our physiological difference, our time on that, we might be able to say it's been 9 Earth months. But if we're going real fast, I'm not talking as fast as we go, I'm talking real fast, like half the speed of light or even 10% the speed of light, we're going to notice that the time it takes to get there for us on the spacecraft is not that long. And that's a huge, huge change because we don't age the same and the time doesn't seem to pass as long. It's a beautiful thought to consider. Now when we get back, yeah, that's a big deal. We have a huge difference in time when we get back. But at least while we're traveling, it doesn't seem so bad. All right, good luck, guys. We'll see you in class. Bring your questions.